In this video, we're going to look at how capacitors behave in simple circuits and how they behave as they charge. So if we have a look at this circuit in front of us here, we have a voltage source, this cell on the left-hand side here, and we also have a switch in our circuit. We have a resistor and we have a capacitor. Now, we know that as soon as we close this switch, this circuit is now complete and the capacitor is going to begin to charge. Now, there are a few factors affecting the rate at which the capacitor charges. First of all, there's the size of the capacitor. A bigger capacitor will take longer to charge. And there's also the resistor in the circuit. The resistor is controlling the flow of current. A bigger resistor is going to restrict the current, and it means that the capacitor is going to take longer to charge as well. So the first thing we can state here in terms of our circuit is something called the time constant. And the time constant is denoted by the letter tau. It's a Greek letter, looks like a sort of curly capital T. So the time constant, tau, is equal to R times C. And so this time constant gives us an indication of how long it takes for our capacitor to charge. And the way that we can effectively measure how our capacitor charges is by measuring the voltage across the capacitor. So I'm going to mark on VC, which is the voltage across the capacitor. If we imagine that we're connecting a voltmeter across it there and measuring the voltage across the capacitor. And that capacitor is going to take a certain amount of time to charge. And the way that that capacitor charges is not linear. So below here, I have a sketched graph of VC against time. So as time passes, what we don't see is a linear increase in the charge of that capacitor or the voltage across that capacitor. We don't see a graph that looks like this, where we have a straight line increase. What we actually see, I'll just remove that, we see what's called a growth curve. And a growth curve has a shape that looks more like this. We see an initial rapid increase and then a sort of leveling out over time. So that's our growth curve there. I'll mark that on there. And the growth curve is an example of what we call a transient response. So the capacitor actually needs a certain amount of time to charge up and then level off as it's fully charged. And this time period is what we call a transient. A transient is just a word for a time of change. And so what we're seeing here is a gradual change in the circuit as the capacitor slowly charges up. One last thing to mention is that our time constant, which we calculated using this formula tau equals R times C, is not the time it takes for the full growth curve to occur. In fact, it probably takes around 5 time constants for the growth curve to occur. So if we calculate the time constant, let's say, as 1 second, then I can assume that it will take roughly 5 seconds for the full growth curve to actually build up and then level off there. So we can say that a full charge is approximately equal to 5 times the time constant. 5 time constants is what it approximately takes for our voltage across the capacitor to gradually increase and then level off. By the time it's leveled off, VC should be equal to Vs in this instance. So if I have a 5-volt cell, for instance, powering this circuit, then I would expect VC to gradually increase up to 5 volts, where it'll level off there once it's fully charged. We can express this growth curve mathematically though. So rather than having to plot graphs and the like, we can express the growth curve using the growth curve formula. And we can express it like this. We can say that VC is equal to Vs multiplied by 1 minus E to the power of minus T over tau. Now, what do we mean by the terms in this equation? Well, first of all, VC we know is the voltage across the capacitor, at any given moment. Now we know that VC starts off at 0 if the capacitor is completely discharged. And as the capacitor charges, it's going to reach the point where VC is equal to VS, the supply voltage. So at any given time, it's going to be anywhere in between the two. Finally, we have 1 minus E, and E represents the exponential function. And E is to the power of minus t over tau. Well, we know what tau is. Tau is that letter for the time constant. But t is the time at which we can take any given measurement. So let's have a look at a quick example. Here's another simple circuit, just like the one we had before. But let's mark some values on this time, and let's say that Vs, the supply voltage, that cell on the left-hand side, has a voltage of 12 volts. Let's say that the resistor R, is a value of 10 kilo ohms, or 10K. And then finally, that capacitor, let's say, has a value of 47 microfarads. And let's say we're asked these two questions here. So question 1, VC at 0.8 seconds. So what's the voltage across the capacitor? 0.8 seconds after the switch is closed. So the capacitor is allowed to charge for 0.8 seconds. And what's the voltage going to be at exactly that moment? Question 2, slightly different. What time is required to allow the capacitor to charge up by 50% of its full capacity? So let's look at question 1 first. And question 1, we can use the formula for the growth curve at the top there. We don't need to plot a graph and determine our results from the graph, because we can just use this growth curve to work out the answer. But before we can do that, we need to work out the time constant. And so the first thing we need to do in our circuit here is use our formula from the previous slide, tau equals R times C. Well, we know that R is 10K, or 10,000 ohms, multiplied by C, which in this case is 47 times 10 to the minus 6 farads. And calculating that gives me an answer of 0.47 seconds. So the unit of the time constant is just a time. It's 0.47 seconds is the unit there. Now that we know the time constant, we can have a go at question 1, because question 1 asks us to work out the voltage VC at 0.8 seconds. So we close the switch, we allow 0.8 seconds of time to elapse, and we want to calculate what's the voltage going to be across the capacitor at that time. So by setting up our equation, we can say that VC is equal to Vs, well, we know Vs is 12, multiplied by 1 minus E, E being the exponential function, to the power of minus t over tau. So minus t, we know the t, the time, is 0.8 seconds. So minus 0.8 over tau, which we said was 0.47. Now, one thing to point out here is that this whole fraction is a power of the exponential function. If you have a good calculator, or a good scientific calculator, there's usually a function on the scientific calculator that looks like this, e to the power of something. And so there's a button or a function that looks something like that, and that'll allow you to calculate this equation quite easily. And also there's a function for a fraction which often looks something like this. And so by using both of those functions there, you should be able to enter this equation into your calculator and calculate the result. But in this case, I've done this already, and I get an answer of 9.81 volts. So what we're saying is, should we close this switch in this circuit, current is allowed to flow, and that voltage, the voltage across C, if I can mark that on very small there. VC is the voltage that we're imagining we're measuring across the capacitor there. VC is going to start at 0 because the capacitor has no charge and so there's no voltage across it. And gradually VC is going to increase to 12 volts in this case. But we're saying that should we sort of stop the clock at 0.8 seconds exactly, then that capacitor should have 9.81 volts measured across it. So now that we've done that, we need to have a look at question 2. Question 2 asks us to calculate the time it would take for that capacitor to charge by 50% of its total capacity. And so the way we're going to judge that is when VC is up to 50% of its full value. We know that VC is going to increase in that growth curve from 0 all the way up to 12 volts. And so at 50%, we know that VC will be at 6 volts. So question 2 is asking us how long is it going to take for that to occur, for us to reach 6 volts on that growth curve. In order to do that, we need to rearrange our growth curve formula because the unknown in this case is going to be T. T is what we're going to try and work out. We know that VC is going to be 6 because we're expecting a voltage of half of the supply, which is 12. And we still know tau, the time constant we said was 0.47 from the previous slide. So we need to rearrange this formula for T. This is quite a complicated thing to do because it involves logarithms. But let's have a go and we'll see what we find in this case. The first thing we need to do is divide both sides by Vs, because if we do that, then we can say that Vc divided by Vs is 1 minus e to the power minus t over tau. We've actually divided Vs from both sides, so we lose Vs off that side and we divide it on this side. So now that we've got this formula, we can also say that we can subtract 1 from both sides. So now we say that Vc over Vs minus 1 equals minus e to the power minus t over tau. And the last thing I can do is I can change the signs on both sides of this formula, because I can say that making that minus into a plus, so plus e to the power minus t over tau, is going to make it minus Vc over Vs plus 1, or I can rearrange those in terms of their order. And finally, I get my equation e to the power minus t over tau equals 1 minus Vc over Vs. We're not quite done though, because the last thing we can do is we can apply logarithms to both sides of this equation. So let's have a look at what that looks like. Here's the same equation that we determined on the previous slide, but we're going to use the natural logarithm and apply this to both sides of the equation. Now, the symbol for the natural logarithm is ln. So by applying the natural logarithm to both sides of this equation, we get something that looks like this. Now, the reason I've applied the natural logarithm is because the natural logarithm is, we can think of it as like being the opposite of the exponential. It'll cancel out our exponential here, which is making this formula a little bit more complicated. So when we do that, on the left-hand side, the logarithm and the exponential cancel out, and it leaves only what was the power of the exponential, minus t over tau. So on the left-hand side, I'm just left with minus t over tau. It's no longer a power now, it's just a normal fraction. And on the right-hand side, we're left with what we had there, the logarithm of 1 minus Vc over Vs. The natural log on the right-hand side there. The last thing to do in this equation is, because we want to find t, the time, we need to get t by itself on the left-hand side of the equation here, and so I'm going to multiply both sides by tau. And so what happens in that instance is we multiply by tau and we multiply by tau on both sides. So we lose it on the left and it appears on the right-hand side. The last thing is to say that we have a minus t left on the left-hand side. We're going to change the sides on both sides of our equation. So minus t becomes plus t, and the logarithm becomes a minus on our right-hand side. So now our final equation looks like this. It's t equals minus the natural logarithm of 1 minus Vc over Vs, and the whole thing is multiplied by tau, our time constant. So let's think back to our original question, because if you remember, we had a 12-volt power supply and we had a circuit that had a time constant of 0.4 seconds. I'll maybe make a note of these on the side here. So Vs was 12 volts, if you remember, and we'd calculated tau, the time constant, to be 0.47 seconds. So now what we can do is, the question, if you remember, was to calculate how long it would take for the capacitor to reach half or 50% of its charge. And so what we were saying is the way we would judge that is we would look for the time it would take for Vc to reach half of the supply voltage, so in that case 6 volts. So now what we can do is we can plug these numbers into our equation here for time. We can say that first of all t equals the natural logarithm, or minus the natural logarithm, of 1 minus Vc over Vs. Well, Vc we've said is going to be 6 and Vs we know to be 12. Multiplied by the time constant, which we said was 0.47 seconds. And if we calculate that, bearing in mind that if you've got a good scientific calculator, it should have a natural logarithm function, ln. But if we calculate that, I get an answer of 0.326 seconds. So what we're saying there is, in this circuit, it would take 0.326 seconds for the capacitor to reach 50% of its full capacity. I hope you found this video useful on how capacitors behave in circuits when they're charging, and how we can represent this in the form of a growth curve and by using the growth curve formula. In the next video, we'll look at how capacitors behave when they're discharging in circuits, and we're going to apply a similar method and similar examples then as well.